Hello Specialist Maths fans, we're going to make a start on chapter 3, circular functions, and to begin with, we're looking at the reciprocal circular functions. Now a couple of problems to think about at the beginning here. The first one says that given tan pi on 2 is undefined, is 1 on tan x defined when x equals pi on 2. Looking at this tan graph on the right hand side here, we can see that when x is pi on 2, tan of pi on 2 has an asymptote, so it's undefined. But the question is, what about 1 on tan pi on 2? What's that going to be? Second one to think about is, if we sketch this graph, y equals sine x over tan x, what does the graph look like at x equals 0? We'll come back to those at the end. For now, we can look at 3a, reciprocal circular functions. We're going to start with sec x secant. We're going to write this as 1 over cos x, and of course cos x cannot be 0 in this case. It's going to be our domain restriction over here. Cosec or cosecant, it's going to be 1 over sine x, and of course in this case sine x cannot be 0. We're not dividing by 0. Over here, we're going to look at cotan, or cotangent. And so because we know that tan is sine over cos, we're going to write cotan as cos x over sine x. And here, we're going to say that sine x cannot be equal to 0. And alternatively, we could write this as, we know that sine x over cos x is tan x, so cos x over sin x we can write as 1 over tan x. Now, considering the denominator here, tan of x, that's sine over cos, we can't divide by 0, so here cos x cannot be 0. And so there's our sec, cosec, cotan. Trigonoidentities. We're just going to start with sine squared theta plus cos squared theta is equal to 1, the Pythagorean identity. And from here, on this left hand side, we're going to think about, if we have sine squared theta plus cos squared theta is equal to 1, if we were to divide all terms by sine squared theta, okay, all three terms, like so, then what we're left with is 1 plus, here we've got cotan squared theta. This is equal to 1 over sine squared theta, which is cosec squared theta. And so in this case, we need sine theta to not be equal to 0, since we divided by sine squared theta. Now, over here on the right hand side, we're going to do division by cos squared theta for all terms. Let's do this, cos squared theta and we're left with tan squared theta plus 1. This is equal to 1 over cos squared theta, which is sec squared theta. And for us, we need cos theta to not be 0. Okay, let's look at some sketching. We're going to look at the standard cosec graph on the left hand side over here. And so to begin with, where our sine curve has x-intercepts, because cosec is going to be 1 over sine x in this case, where our sine curve has x-intercepts, this is going to be a 0 denominator, and we'll have an asymptote. So here, 1 over 0, asymptote. There we go. Over here, at x equals pi. Over here, x equals 2 pi. Over here, x is minus pi. And over here, x equals minus 2 pi in terms of for the domain that we can see here from minus 2 pi to 2 pi. I'm going to put my equations for my asymptotes, of course. Minus 2 pi minus pi 0 pi, and finally 2 pi. Now I'm going to consider the period. My period of sine is 2 pi. That's going to be the same period for cosec. Let's get a look over here where, for example, if we look at pi on 2, sine of pi on 2 is 1. That means that cosec is going to be 1 divided by 1. So it's going to be 1. Because the period is 2 pi, I'm going to repeat over here. Okay, at minus 3 pi on 2 and 1. We're going to look over here at 3 pi on 2. Sine of 3 pi on 2 is minus 1. 1 divided by minus 1 is minus 1. So here is an intersection between sine x and cosec. Similarly, I'm going to shift 2 pi to left over here, and we've got another known point on our cosec graph. I'm just going to choose one more point. Let's say we've got pi on 2 here. I'm going to look at pi on 4. We know that sine of pi on 4 is 1 on root 2, and so 1 divided by 1 on root 2 is going to be root 2, which is about 1.4. So here at pi on 4 and about 1.4, we've got a point here at 3 pi on 4 and 1.4, we've got a point, and now we're going to draw a nice curve. Let's try that again so we can get that a bit nicer. Okay, and we're going to exhibit asymptotic behavior. We're just going to repeat that on this left hand side. I want to approach my asymptotes but not touch them and not move away from them. And then now if I look at something like here we've got 3 pi on 2. Okay, if we look at 5 pi on 4, we can see that sine pi on 4 is going to be negative root 2, so it's about here. And sine of 5 pi on 4, 7 pi on 4 is going to be minus root 2, so it's about here. And so if we have a curve as such over here. I might do that one again. Approaching the asymptotes, never moving away from them and not touching them. And lastly, on the left hand side of our graph over here. Okay, so that's our cosec graph. When we look at, on the right hand side here, this sec graph, what we notice between the sine curve and the cosine curve is that for this sine curve, if we move this pi on 2 to the left, we get the cosine curve. And so similarly, if we move our cosec graph pi on 2 to the left, we're going to get a sec graph. And so all these asymptotes I'm going to move by pi on 2 to the left. So for example, instead of x is equal to pi, it's going to be over here at x equals pi on 2. X equals 3 pi on 2. X is negative pi on 2, and x is negative 3 pi on 2. Label all these, of course, with their equation. Minus 3 pi on 2. Minus pi on 2, and finally 3 pi on 2. And now, similar to before, because sec is 1 over cos x, if we consider our values for cosine, for example, here at x equals 0, cos of 0 is 1, 1 over 1 is also 1. This is going to be a common point. And in fact, of course, it's just our cosec graph, but shifted pi on 2 to the left. As such, and we're just going to draw our endpoint here. And our final one on the left hand side over here. Okay, so we've got a cosec graph and a sec graph. Moving down here to our cotangent. Draw yourself a table. As such, we're just going to look at using this table to help us in sketching our cotangent graph. So if I'm looking at sine x, sine of 0 is 0, sine pi on 4 is root 2 on 2, sine pi on 2 is 1, sine 3 pi on 4 is root 2 on 2, and sine of pi is also 0. I'll fill in for cosine. Cos of 0 is 1, cos of pi on 4, root 2 on 2, cos pi on 2 is 0, cos 3 pi on 4, minus root 2 on 2, and finally, cos of pi is minus 1. And so, if we think about cotan as cos of a sine, here, this is going to be undefined, 1 divided by 0. It's not going to give us anything. Here, root 2 on 2 divided by root 2 on 2 is going to give us 1. I've got 0, I've got minus 1, and again I've got undefined. And so I'm going to plot these. So when x equals 0, we're undefined. That's going to be an asymptote. Also, at pi, asymptote. At negative pi, asymptote. Equations, of course, minus pi, 0, and pi. And so some other points we have is pi on 4 is going to be 1. That's going to be an intersection point. We've got pi on 2 is going to be 0. That's our x-intercept. We've got 3 pi on 4 is minus 1. Another intersection point. And so from here we can draw our cotangent graph. We've got asymptotic behavior, of course, approaching the asymptote, never moving away from it, but not touching it. Like so. And we're going to repeat for the same period of pi over here on this left hand side. Not thrilled with my shape there, going a little bit away possibly from the asymptote, so I'm going to fix that up. Okay, that's going to have to do. Okay, so there's a cotangent graph. Now down here it says, but shouldn't cotan pi on 2, which according to our graph is 0, if that's equal to 1 on tan pi on 2, where we know that tan pi on 2 is 0, shouldn't be this undefined. Same question we got before, but we can see that it's 0, so that's interesting. We'll come back to that at the end. And so I've got a couple of examples. Here's the first example. Between 0 and 2 pi, we want to sketch y equals sec x minus pi on 4. We've got to do axis intercepts, endpoints, turning points with coordinates. We're going to do asymptotes with their equation. Now when I see this, I'm essentially seeing a sec curve, but we've gone pi on 4. we've shifted pi on 4 to the right. So where's our sec curve? Over here. Okay, so everything's going to go pi on 4 to the right. I like to start with the first asymptote. So this first asymptote is at pi on 2. It's going to move pi on 4 to the right. So it's going to move to 3 pi on 4. So I'm going to start with that one. Let's say over here. That means that my next asymptote will be at 7 pi on 4, because our period is going to be 2 pi. Okay, I'll label these, of course. Three pi on 4, 7 pi on 4. Pi on 4, that's a bit better. Okay, now in the middle here, we're gonna have, well, you can start where you want, but I'm just gonna focus on this part, because normally my cursor curve will look like such, and then here, I've got my maximum turning point, and that's gonna be right in the middle. Okay, it's gonna be here at 5 pi on 4, and minus 1. And in fact, I can do my sketch already. It's going to look something like such. Okay. And so, if I look at this left-hand side, I know that if I go pi on, if I go pi on 2 to the left of pi on 4, that's going to be my minimum turning point. So that's going to be about here. Okay, that's going to be at pi on 4, 1. Okay, I'm going to come up as such. And then over here, I'm going to have a y-intercept. Obviously, we'd try that again. We're going to have a y-intercept. Now, what's the y-intercept going to be? We're going to sub in 0. We're going to get sec minus pi on 4, which is the same as 1 on cos minus pi on 4. Cos minus pi on 4 is the same as cos pi on 4, which is 1 on root 2. And because we're doing 1 over 1 on root 2, this is going to be root 2, so 0, and root 2 is our endpoint over here. Now, because the period's 2 pi, I'm going to come over here to 2 pi, and this is going to be 2 pi and root 2. And this is going to, if you like, because I'm doing one cycle, this is down, up, this is the maximum turning point, and so this is the remaining left-hand side over here. Something like that. Okay, so I'll just quickly check, have I done everything that I need to do? 0 to 2 pi, yes. Axis intercepts, I only have a y-intercept. Endpoints, yes. Turning points with coordinates, yes. Asymptotes with their equation, yes. Okay, last question then, example 2. If tan x is equal to minus 5 and x is between minus pi and 2 and 0, so i.e. that's in quadrant 4, then find sec x. Okay, so from above, we had something like, let's say if we had, now I wouldn't do this, but you could do this, for example, if I had sine squared x, okay, plus cos squared x is equal to 1. Now because I'm trying to generate sec, I could divide everything here by cos squared x. Okay, and so over here, that's going to give me tan squared x plus 1 is sec squared x, which is our identity from before. And because I want to find sec x, okay, I'll write this as the square root of tan squared x plus 1. And so now I'm going to substitute in tan x, which was minus 5. We need to square that. Plus 1 and square root it. So this is equal to plus or minus root 26. However, let's just draw a unit circle like this. We're in quadrant 4, we're here. And so because sec is 1 over cos, we are going to be positive here. And so therefore my final answer is sec x is root 26. Now, that's one way to do it. I probably wouldn't do it that way, to be honest. I personally would do something like this. So let's say alternatively, okay, I would probably do this, draw a 90-degree triangle, or try to draw a 90-degree triangle, and if this is x, they've told us that tan x is minus 5. So if I do 5 here, if I do 5 here, and 1 here, tan of x is 5. I can then use Pythag to figure this hypotenuse out as 5 squared plus 1 squared all square rooted. And now because I want to find sec of x, okay, which is 1 over cos. Cos is adjacent over hypotenuse, and so if I flip that, sec is going to be hypotenuse over adjacent. Which from my triangle, the hypotenuse is root 26 and the adjacent is 1. And because I'm in quadrant 4, that's my answer. So that's probably how I would do that question myself, but either's okay. Now to finish this off, cos of x, well, I'm just going to look at my triangle. Cos of x is adjacent over hypotenuse, so it's 1 on root 26. I will rationalize denominator, so root 26 on 26, and because we're dealing with cosine, we're in quadrant 4, so it's positive. That's my final answer. And so this last one, cosec, if I'm thinking about cosec, it's going to be 1 over sine. Now sine is opposite over hypotenuse, so cosec is hypotenuse over the opposite. Look at my triangle, this hypotenuse was root 26 and the opposite was 5. I'm going to consider cosec is 1 over sine. In quadrant 4, sine is negative, so my answer is minus root 26 on 5. Okay, so back to the first question. Given tan pi on 2 is undefined, is 1 on tan x defined when x equals pi on 2? And so when we drew a graph, okay, for cotan, it was 0. Right here, it was 0. And so what are our options here? We can think of this as, see if I can draw here. This is 1 divided by sine x on cos x. Okay, which is going to be cos x on sine x. Now we're going to consider what's cos pi on 2. Cos pi on 2 is going to be 0. Sin pi on 2, that's going to be 1. And so in this case, we get 0. Now, that's one way to look at it. In terms of if we do some simplification, we can get 0. Okay. Alternatively, you can look at it with limits, which is a little bit more complicated. But I think just quickly, if you looked at it in terms of limits, what we're going to say is like, what's the limit of x as it approaches pi on 2 from the left-hand side for our function as such. And so from my graph here, this is pi on 2. As we approach it from the negative direction, from the left-hand side, this is going to approach infinity in terms of tan x. And so 1 on tan x, okay, that's going to be 1 on a gigantic number. And as we have 1 and divide it by a really large number, that approaches 0. And similarly, if we look at the limit from the right hand side, so if I write this, the limit as x approaches pi on 2 from the positive direction, 1 on tan x, okay, this approaches negative infinity. In terms of tan x, 1 divided by a really large negative number is also going to approximate 0. And so because our limits as we approach pi on 2 from either side approximate, or the limit is 0, we can conclude that therefore the limit as x approaches pi on 2 for 1 on tan x, this is equal to 0. And let me just grab the calculator, let's have a look at this. 1 on tan x, given that x is equal to pi on 2. Yes, we do get 0. So that's interesting. Now, this last one, if we sketch y equals sine x on tan x, what does the graph look like at x equals 0? Because if we look at this, tan of 0, that's 0, so we can't divide by 0. But what does the graph look like? Do a quick graph. This is going to be sine x over tan x. Okay, so when x equals 0, it kind of looks like that. But if I will trace, okay, if I trace my graph when I get to 0, it's actually undefined there. Interesting. Let me just do a zoom in here. Have a look at this. It kind of looks like as if it's there, but when I try to go there, undefined. Okay, and so this is a hole in the graph. Okay, so when we would draw this, we're going to have an open circle here at 0, 1. Now, how do we get the 1? We could do, for example, sine x divided by tan x, which is sine x on cos x, okay, which is going to be sine x times cos x on sine x. So it's just going to be cos x, and we're going to be doing cos of 0, which is 1. So in terms of our graph, we can actually say that the limit as we approach x from either direction is 1. Okay, but because we cannot substitute 0 into our original function, it's undefined there and we have a hole.